Good morning, Astronomy 1010. Welcome to part 2 of lecture 8, our second part lecture on the sun. We are going to delve through the layers of the sun today, and if we're lucky, get to the heart of our own star where nuclear fusion powers the energy that eventually becomes this wonderful sunlight that is so welcome to us after so many months of winter. When we last left off, we were talking about the ideal gas law. So what's the ideal gas law all about? Tell me what you know. I want to ask you some questions to make sure that you're ready to proceed. Jenna, we might need you to hold it down here.
Yep, so the ideal gas law is P equals, so pressure equals number density times temperature times Boltzmann's constant.
That's right. Watch out for this, guys. We now have two constants of nature from physics that have the word Boltzmann in it. There is the Stefan Boltzmann constant, which we use for blackbody radiation, and there is the Boltzmann constant, which we use for gas particles. Sorry, Boltzmann did too much creative, cool work, and now we have to get confused, okay? So there's two constants. This constant, the Boltzmann constant, we're going to see a whole bunch of times in our remaining lectures. So don't think this is like going away. The Boltzmann constant shows up anytime we deal with gas particles. And of course, what we're doing right now, guys, is not only are we learning about the sun, which is a giant ball of gas, but we're eventually going to want to talk about planets. And when we learn about planetary atmospheres, obviously gas dynamics are going to come into play. Okay, so pressure is number density times Boltzmann constant times the temperature. Really, it's a relationship between three quantities. Pressure tells you how hard the gas particles smash into each other. Number density tells you how many particles there are in the box. And the temperature sort of tells you like the speed of the particles. I used to have this absolutely wonderful flash program for the ideal gas law, and it's no longer working, and it's causing me a lot of distress. Just a moment here. Instead, I suppose we'll have to settle for a less impressive animation. This one here, slide 22. Wow. Guys, hold on a second. I'm just going to pause this recording. I'm having some technical difficulties here. Just give me one sec. Okay, let's see if we can do this again. I wanted to show you guys a little animation of an ideal gas, one that I shared with you before. I think it's slide 22, function F522. Boom. Okay. So these could represent the atoms that make up the gas inside of the sun. And you guys know that the sun is a mixture of primarily which two gases? Jenna, I don't know if these guys actually got to watch the Monday lecture yet, so I might have to rely on your expertise now.
Yep.
It's made up of hydrogen and helium.
Hydrogen and helium, very good. So what are the ratios? That's something I would test you on. I would test you on what?
70% hydrogen and 28% helium.
Nice, Nori. I'm impressed. Okay. That means if we look at this box, the blue pellets would be hydrogen atoms. The red pellets would be helium atoms, okay? The temperature of the gas is related to their kinetic energies and therefore their speeds. The pressure is the force of the particles smashing against one another. Can you guys remind me what the units of pressure are? Because if you don't know your units, it's kind of like you don't know anything, you know? What are units of pressure in the MKS system?
Oh, I was going to say Pascal.
Pascals. Very good. Pascals. Okay. Okay. This is just me kind of jogging everyone's memory to kind of where we left off, okay? I was teaching you guys about the ideal gas law. And like I said, I used to have this really cool animation with like a bicycle pump, and you could pump the particles into a box, and it was just really funny and dorky and cool, and I'm really depressed about it, so I'm just complaining. In any case, it's time for us to think about the sun itself. The difference between gas particles in a box and the sun is that in the sun, there is no box. The gas particles are inside a massive and very large sphere. You can see it glowing on your sky, and there is no bag or boundary that surrounds the sun. And yet, as you can see with your own eyes, the sun maintains a perfectly fixed radius. Forgive me if I said this last class as well, but if you lived on a planet around the star Polaris, Polaris is a pulsating variable star, and that sun would actually grow and shrink over the course of 1 month in your sky. That would seem very bizarre to us, but there are some stars that do not maintain a fixed radius. Why does our sun maintain a perfectly fixed radius? Gas particles just want to blow away into space, right? What do you think makes the sun such a perfectly fixed round ball? Say that, Jenna?
Oh, I was going to guess, is it the sun's gravity?
That's right. And if you think about it, Jenna, the gravity must be in such a perfect state of balance with the pressure of the gas particles that the sun maintains a perfectly sharp, perfectly fixed radius in our sky. And this is an important concept in stellar astronomy. It's called hydrostatic equilibrium. And it's a key buzz concept in astronomy because it tells us why the sun maintains a fixed radius, but it also relates to planets like Jupiter and Saturn, which are essentially giant balls of gas. This is a noteworthy topic, so let's do it. Okay, introducing a concept called hydrostatic equilibrium. Oops, IUM. Hydrostatic equilibrium is a balance of forces between gravity, the sun's gravity, pulling, shall we say, in, the sun's gravity is pulling inwards, and what we would call thermal pressure pushing out. And we use the word thermal pressure to say that it's the pressure related to temperature, or in other words, it's the pressure expressed in the ideal gas law. One of the reasons we have to mention thermal pressure as opposed to just pressure is it's possible for gases to have pressure that depend upon other factors. Like, for instance, if you squeeze a gas so hard that the atoms are pressed up against each other and have no more intermolecular space, the atoms become degenerate and enter a quantum state. The hearts of stars are degenerate and they behave very strangely. The gas that makes up the majority of the sun is just like the gas inside some blown up balloon. It's in a state of pressure, or it has pressure that's balanced by gravity. Okay, before we go into the layers of the sun, I want to have a little quick tidbit on the sun's energy generation methods. May I erase? Okay. Do any of you know from life, or because you saw it in a TV show, how old the Earth or the solar system is?
I want to say the Earth is like 4 billion years old, right? Or a little more.
Closer to 5. It's
Okay.
actually 4, but good. You had it in the several billions of years. It's our best measurement to date is 4.6 billion years. Let's write this down. This is a cool tidbit to know. So the age of the sun is equal to the age of the Earth, and it's equal to the age of the moon, and it's equal to the age of the solar system. And what that means is we believe the entire solar system formed at one time. There's even a name for it. It used to be called the Nebular Hypothesis, but today it's known as the Nebular Theory because we have so much evidence that stars and solar systems form in this manner. And the current best estimate of the age of the sun, or any of these one things, is 4.6 billion years. You might wonder how we could know such a thing. In fact, I want to kind of shock you, Ian, with the amount of precision that we believe we know the age of the solar system. Watch this, guys. If I type into Google, you know, what's the age of the solar system? According to, you know, one of these websites that Google has trolled through, they're quoting it as 4.571 billion years. That blows my mind. That means they're extremely confident that it's 4.57, and there are some scientists that are arguing over the fourth decimal place of precision. We know the age of the solar system to a 1 part in 1,000 precision. One of the ways we know the age of our solar system the classic way is during the Apollo moon landing, astronauts sampled many different moon rocks and brought them back to Earth for analysis. As you will learn when we study planetary science, the moon is different than Earth in that the moon solidified and it formed at the beginning of our solar system. But because it's so small and because it lacks any atmosphere or geology, the moon is sort of geologically dead. And except for the occasional impact crater that smashes into its surface, these rocks would have cooled at the start of our solar system, and they've been sitting in space, preserved in vacuo, since the beginning of the age of our solar system. When astronauts sample chunks of moon rock, they can measure isotopes of uranium and deduce how long it's been since the surface of the moon rock cooled. And the argument is the age of the moon rocks will be approximately the age of the entire solar system, and therefore the age of the sun. So I think that's interesting. I don't know if you do. Here's another interesting tidbit to think about. The sun has been shining with more or less a consistent luminosity for all of this time. And there are many different ways to deduce this. One way is just to study things like fossil records of ferns. Let's just type in fern fossil. Of course, the fern from millions of years ago is not going to be completely identical to the fern today, but from what I've read and understand, ferns really haven't changed too much in their design for millions and millions of years. And one of the ways you can go about things like this is a biologist can look at a fossil record of a fern etched into a rock from tens or hundreds of millions of years ago, and they can pretty much estimate that if the fern leaves are similar to the size of the fern leaves today, the sun would have to have been shining with the same intensity for this plant organism to maintain the energy supply it needs. In other words, just like ferns need a certain amount of sunlight today to live, so did the fern of 10 million years. And there are other things you can do, more elaborate methods, to deduce that the sun has been shining for all of this time. The sun has been shining with a luminosity of 4 times 10 to the 26 watts for all of these years. So a question that scientists had asked themselves throughout the history of solar astronomy is, how? How does the sun pump out so much light for so many billions of years? There are 3 different concepts that I want to take you through because I think it illuminates some aspects about this class. I would like to erase this with your permission. I'm going to need some board space. Okay. The first thing I'd like to talk about is fire. The sun is not a ball of fire. And this is worth mentioning because all throughout history, poets and artists and other bamboozlers of the human soul have referred to the sun as Helios in his fiery chariot marching across the sky. Poets can lead us on flights of fancy that are not always truthful, right? That's sort of how they make their money. Ooh, sorry, I'm having some focus issues here. Let me see. This might knock out the audio for 1 second, but I'm gonna activate that Logitech thing so we get our focus under control. Bear with me, guys. It takes a very long time for this dum-dum to load. Okay, here we go. All right. So why is the sun not a ball of fire? Because fire is a chemical reaction. And because at some point today I want to talk to you about nuclear reactions, I'd like you to consider the following operation here. Let me grab my slideshow. Okay, tiptoe through. Let's think about what fire is, okay? So let's imagine we've got a couple of different molecules. These little red pellets that you see, that's diatomic oxygen. It's two oxygen atoms stuck together. Some of the air that you are breathing in this room contains oxygen, only about 21%. Oxygen is a very violent and combustible atom or molecule. It's hungry for electrons. It'll strip them off of anything. That's why you can use it to power your cells. If you take 2 parts diatomic oxygen and you mix it with this molecule of methane, a violent chemical reaction takes place and emits light. You call that fire. And then the atoms swap their dance partners. The hydrogens tear themselves away from the carbon. They bond to the oxygen, making this popular molecule, H2O, water. And then the carbon is left over with the 2 kicked out oxygen atoms. This is a chemical reaction. You've exchanged electrons and you've changed the dance partners of your atoms, but the atoms themselves did not change. Hydrogen on the left is still hydrogen on the right. Oxygen on the left is still oxygen on the right. This is the difference between chemistry and nuclear physics. In chemistry, you swap atoms and molecules. In nuclear physics, you bust the atoms themselves apart. You screw up their nuclei. Let's say for some reason, you could create a massive ball of oxygen and methane in just these ratios. Imagine you had a huge pile of gas floating in space, just like the sun, but it actually was a huge ball of fire. You can quickly calculate, and you will do so in your homeworks with me today, that if the sun had to shine at a luminosity of 4 times 10 to the 26 watts through fire, the sun would burn itself out in a time scale of order 10,000 years. And early chemists knew this. They knew that if you had a huge ball similar to the mass of the sun, and it were to pump out this much light, that it would use up all of the chemical reactions in 10,000 years. And that's clearly not even old enough to explain fern fossils, stratified layers of geology, bones of dinosaurs, anything like that. The sun could never have been a ball of fire. Another possibility of how the sun might generate its light is through something called gravitational contraction. And this is very closely related to hydrostatic equilibrium. Gravitational contraction just means that when the sun first forms, gravity takes some huge extended nebula, it slowly pulls the atoms together and assembles them, and as it squeezes the ball of gas, so here's gravity squeezing down on a ball of gas, and as you do so, that ball of gas will become hot, and as that ball of gas becomes hot, it will act like a blackbody, and it will begin to shine. When our sun first formed 4.6 billion years ago, it had not quite turned on nuclear fusion in its core, but it would have shined and been just as brilliant and bright as the sun today. In fact, some protostars even have luminosities greater than the eventual star that they become. Even something like the planet Jupiter or the planet Saturn, Neptune, Uranus, when they first formed, they would have been glowing bright hot. Man, it would have been cool if we could take a GoPro and travel back 4.6 billion years ago into the early solar system. Not only would you see the sun glowing in our solar system, but all the other planets would be shining light as well, like all of these brilliant fiery points going around each other. Gravitational contraction can actually sustain a light output similar to the sun's for a time scale of something like 100 million years. Now that calculation we will not do in our homeworks today because this is a little bit over your pay grade. But an astronomy student at the junior or senior level frequently has to make this calculation. It's not super hard, it's just a little too time consuming for us. So we can't power the sun as a ball of fire, and we can't power the sun through gravitational contraction, because what will happen is over 100 million years, the sun will radiate away all of its light, and then it's going to look like Jupiter. Oops, excuse me. Ooh, a giant ball of gas that's not glowing. So how can the sun sustain this light output for 4.6 billion years? I've already hinted at what the answer is. Do you guys know? How does it do so?
I probably wouldn't be able to explain it very well, but nuclear fusion, right?
That's right. And this is a sort of a logical thing you have to go through, that the sun continues to power this light output through the method of nuclear fusion. And as we go into the heart of the sun, I want to take some time to explain this. I don't know if I can get through all the layers today because I'm going kind of slow and I'm having fun, but I'd like to get there. Nuclear fusion basically works through Einstein's famous E=mc² equation. You can learn about this equation in the other version of my course, Astronomy 1020. Here's a pitch. Also satisfies a 4-credit lab science and is available during summer 1. And I would love to have some of you students come back for more punishment with me. Also, P.S., the second part of this course is kind of like the first part of this course, so you're kind of already trained, and that means it's not too hard. Anyways, now that I've made that pitch, consider this. Until Albert Einstein discovered this equation in 1915, astronomers, before they knew that nuclear fusion was possible, didn't actually know how the sun continued to shine for so long, and they were confused as to whether the Earth actually could be billions of years old, because they couldn't comprehend how this would happen. Now, in the sun's core, nuclear fusion, and I'll explain this later, proceeds by taking 1, 2, 3, 4 hydrogen nuclei, that's 4 protons, and essentially smashing them together to create a helium nucleus, 1, 2 protons, and 2 neutrons. So basically you change and transmute 4 hydrogens into 1 helium. And when you do this, you actually have to shave off and kind of destroy a tiny little bit of mass. Destroy, of course, isn't the right word. You convert a little bit of the mass of these protons into light in the form of gamma rays. So the famous equation that powers the nuclear fusion in the sun, the net reaction is 4 hydrogens collide to make 1 helium and 2 gamma rays. And this, my friends, this is what eventually becomes the sunlight that leaks its way through the star. Fusion cannot proceed in every part of the sun, only at its very core, where the temperatures are absolutely berserk. Are the temperatures high enough for this reaction to proceed? In a way, once you start generating these gamma rays, they then wiggle their way through the star and they help heat it up and support hydrostatic equilibrium. So this is actually a secret component to hydrostatic equilibrium. By the way, today in your homeworks, you will calculate how long the sun can sustain its luminosity using nuclear fusion, and you will discover that the time scale associated with nuclear fusion is 10 billion years, which is totally wild because it suggests that we are halfway through the sun's life and that the sun has another 5 billion years to go. I think that deserves a sip of water on my end. Okay. So what do we want to do next if we want to learn about the sun? We want to learn about how energy transports itself from the core out to the surface. And we want to study the sun as kind of like a layered cake in which things are happening differently at different levels. In other words, I want to take you bit by bit, 29, through the different layers of the sun and kind of explain to you guys how energy is moving from the core to the outer layers. Now, people that I did not see on Monday, Kim, Nori, Ian, did you get to see any of those cool videos that I showed the class on Monday of the, of the magnetic fields on the surface of the sun?
No, like I said, I'm gonna do it right after this class.
Okay. But Nori,
Yeah, I got to see them.
you get to see them. How about you, Kim? Okay. Okay. So you remember that the layers of the sun that we can directly observe are the corona, the chromosphere, and the surface layer, the photosphere. And I'm not sure if you guys remember what it looks like, right? But just for, I guess, for the benefit of Ian, so he can follow us, let's quickly go to slide 3. Oops. This is what the surface of the sun looks like, Ian, at visible wavelengths. It's a perfectly uniform and boring yellow ball. If we change our wavelength of observation to ultraviolet or X-ray wavelengths, we suddenly see all these different things. We can see the upper atmosphere of the sun. We can see these loops of magnetic fields. I particularly love this video, which I believe is right on the border of X-rays and ultraviolet, where you can really, in fact, I want you guys to notice something. Notice that the surface of the sun in this video is actually black. You can see that the ball of the sun underneath it is black because the surface of the sun does not generate X-rays. It's the upper atmosphere that generates X-rays. So we can see different layers of the sun in different processes by studying these different layers. Okay. Let's make a 6-layer cake that is the sun, and I've got lots to say about each layer. We're going to make a kind of analogy with planets because planets is something that we kind of intuitively understand. 6 layers of the sun. The outer 2 layers, which you could think of as the atmosphere of the sun, are the corona. Relationship to the coronavirus is that corona means crown. And the chromosphere. Taken together, both of these represent a wispy outer layer of the sun. And I tend to think of both of these layers as sort of like the atmosphere of the sun. It's a loosey-goosey analogy. The difference between them mainly lies in their temperatures. The corona has a mind-bogglingly hot temperature of 1 million Kelvin. That is not hot enough for fusion, but it's hot enough to make your gas completely ionized. The chromosphere is maybe 10,000 Kelvin. And both of these have the same sort of definition, okay? What are they? They are low density, yet extremely high temperature plasmas that are ultimately being heated by the magnetic field activity at the outer layers of the sun. They're heated by magnetic field, you might call them storms. They're twisting and winding magnetic fields that heat up the plasma. did we talk about a plasma last time, Jenna? I can't remember if I gave you guys that spiel. So what did I
Yes.
tell you? What did I tell you about plasmas? Let's remind Ian, who hasn't seen the video yet.
We said that plasma is a charged gas, and it is primarily found. It's what makes the sun very hot.
No. Sorry, plasmas don't make the sun hot. Hot makes the plasma.
Okay.
Does that make any
Yes.
sense?
Yes, that makes sense.
Because Nori, if you heat up a gas, you cause the
Jenna.
electrons to jump into higher and higher orbits, and eventually, at some temperature, they jump off the atoms, right? So heating a gas makes it a plasma, not the other way around. Okay. Did I tell you that the sun was a mixture of neutral gas and plasma?
Yep. Yes.
So which layers, what part of the sun would we find the most neutral gas then, Jenna?
The most neutral gas would be at the atmosphere
No.
or at the corona.
No. This is a completely 100% ionized plasma at 1 million Kelvin. Okay, so this is somewhere where I failed, so we're going to fix that. Where you find the majority of the neutral gas is at the next layer down. I'm just going to erase this little definition here. I'll come back to this stuff later, okay? I just kind of want to make an overview of the layers, and then we'll try to zoom in on them. The next layer is the coolest layer of the sun. It's called the photosphere. And the photosphere is kind of like the surface of the sun, but it's not a physical surface the way Earth has a hard surface. It's actually just a thin layer of gas. But the reason why it looks like the surface is this is where all of the visible light is produced. And that's actually how we define the photosphere. The photosphere has a key temperature of 5,800 Kelvin. It's extremely uniform. And we define the photosphere as that layer from which visible light is emitted. And when I say visible light, you know, I mean Roy G. Biv, 400 to 700 nanometers, right? The rainbow. It's that layer from which the visible light is emitted. I got a lot to say about the photosphere. I'm debating how much I want to say. Let's start by saying this. Compared to the radius of the sun, it's super thin. It's only 50 kilometers. I'm going to start by writing thick, because that's how we usually say it. But I'm then going to cross out using strike through thick. And I'm going to write 50 kilometers thin to remind you that 50 kilometers is a very, very small percentage of the radius of the sun. Let's take a quick look at the photosphere once again. This opening picture is a picture of the photosphere. This is also an image of the photosphere. Notice that the illumination is extremely uniform with only blemishes from sunspots. I'd like to show you another picture of the photosphere, just a couple of different images to give you a sense of it. Here's a great classic picture of the sun's photosphere in slide 37. Oh, sorry, I hit a funky button. Okay. This surface is glowing uniformly. In this picture, it looks yellow, probably because it was taken with a filter down on Earth with an Earth-based telescope. If you were actually in outer space and you could handle staring at the sun, its surface would appear perfectly white to you. Or at least, yeah, actually, it would be pure white. I mean, absolutely pure white. What generates this light is the same thing that generates this light. The sun is glowing just like the gas in this lighter. Do you guys know what the spectrum? Did we talk about this during our light chapter? What is the spectrum of a candle flame?
I vaguely remember. Was it emission? Or I know someone guessed that, and then it wasn't. Oh no, it's I do know.
You take
It
good
was
notes. Jenna. Like,
continuous. It was a continuous spectrum.
it's a continuous spectrum. So what does that suggest? So I just want to see how much you know about this physics stuff here. So this is a continuous spectrum, a rainbow. So according to Gustav Kirchhoff, what causes a rainbow? What causes a continuous spectrum?
A hot, dense solid.
Does this look solid to you?
No.
And yet it is still a black body. The gas in this room, by the way, the gas in the photosphere is like a tenth. It's like a tenth as dense as the air in this room. The photosphere is actually lower density than the air in this room, and it's still dense enough to glow as a black body. And what does black body mean? It means I glow because I'm hot. Now, in a few moments, I'm going to try to explain to you that these layers are not black bodies. That is not why they glow at their own unique wavelengths. And these guys, well, the truth is complicated. I want to say they don't glow at visible wavelengths, but they do a little bit. The photosphere is powered by thermal black body radiation. And what that means is it means that the surface of the sun that you see with your eyes, when the sun's glowing in the sky, it's caused because the gas is hot. Do you see how that might be confusing to a student? Because I just went and told you that the sun's not a ball of fire, right? And yet the gas at the photosphere glows essentially in the same way that fire does. But here, the reason why this chemical reaction takes place is because I have some butane, or I don't know what's in there, probably butane, and I light a spark, and the oxygen plus the butane basically make a chemical reaction like the one you just saw, right? But in the sun, it's hydrogen and helium gas that's so hot because energy is leaking up from lower layers of the star. It glows then like a hot gas, or sorry, like a hot dense solid that's still a gas. In fact, here's something interesting about the photosphere. If you go and you take a high resolution telescope and you zoom in on a little patch of photosphere, you discover that it's not as uniformly glowing as you at first thought, but that at up close levels, the surface of the photosphere is modeled with a whole bunch of little bubbles that we call granules. And for scale size, each one of these granules is approximately the size of the state of Texas. So these are Texas-sized bubbles bubbling up from below on lower layers of the sun. The bright bubbles have just recently risen to the top, and now the gas is thin enough for the photons to shoot out and escape into space. And as the little bubbles shine their light away, they become cooler, darker bubbles. They get a little bit darker and they sink back down. This is called granulation, and they're like little light bubbles that deliver light to the surface. Let's write that down in our notes. The photosphere contains granules. These are Texas-sized blobs of hot and cool gas. If I felt like writing down even more notes, I might write that granules deliver light to the surface of the star, but I don't feel like writing that down right now. Maybe you'll accidentally remember it or something. Do you guys remember from our Monday lecture how big a typical sunspot is?
About 4 times the size of Earth.
Yeah, the very biggest ones. But in other words, Jenna, granules are Texas-sized blobs, and we do find sunspots at the photosphere as well. Sunspots are Earth-sized blobs, also of of cooler gas. I think I need to switch markers here. I'm burning this one out. Before I open up a fresh one, let me see if any of the, no, that's totally dead. That's totally dead. I'll throw those out later. Wow, that's totally dead. Time for a freshie. All right. Earth-sized blobs of cooler gas. The difference between granules and sunspots is that the sunspots is gas which has been trapped by magnetic fields. I'm trying today's lecture a little bit differently than I do my typical sun lecture. Usually when I give a lecture on the sun, I kind of zoom into each of these layers and I get kind of lost in the sauce and we try some exercises. But I know that today we have to do a homework on the sun that's going to cover like a wide variety of topics. So I'm kind of bouncing around here. And I hope that later I'm going to be able to zoom in and try some exercises with you on these different layers. But this will be an experiment. I would like to, while I'm talking about this, show you an iconic picture of granules versus sunspots. And I think this is from the older TRACE satellite. I've seen this picture just popping up in different astronomy textbooks. And at some point I realized it was a good, useful picture because this picture has been exposed such that you can see sunspots here and you can see blobs and granules there. And you can really get a sense of the different scale size, right? You can see that the sunspots are much darker and much larger. Now, the granules are just the natural bubbling pattern of the sun, hot bubbles rising and sinking. This is something totally different. Basically what's happening, and I need to explain magnetic fields a little bit better to you guys, but what's happening is the magnetic field lines that poke out of the sun, they trap plasma. They freeze plasma to the magnetic field lines, kind of like flies sticking to fly paper. And as the magnetic field lines trap plasma here and here, they stop the bubbles from rising up and down, and they kind of arrest the gas right up at the upper top of the photosphere. And that gas can now shine away its light into space. And it keeps shining and shining and shining and shining, but it can't sink back down into the sun. What's the result? Eventually, after shining for many, many hours, the gas becomes so much cooler than the surrounding gas that it actually starts to look black because it's giving off so much less radiation. In fact, sunspots are kind of cute because they're formed by magnetic fields. Sunspots always come in pairs. There's usually a north and a south pair for every sunspot. They rotate and travel around the sun, which we're going to use to measure the sun's rotation in our next lab. And the sunspots kind of come and go with the sun's 11-year magnetic cycle. The sun has like a period of 5.5 years with lots and lots of sunspots, and then 5.5 years with no sunspots. And you can actually see this if you go and look at the Solar Dynamics Observatory website. We're currently at a solar minimum, SDO. You know, something really strange happened. When we looked at the sun last time, they did not have a picture posted for that day. Let's see if they've since. Do you remember that, Jenna, when that happened? That actually blew my mind. I had no idea what was going on there. So today's date is 3/24. You can see it's back, Jenna. Okay, that was a really weird thing. I still have no idea what that was all about, but you can see, Jenna, this picture was taken today, March 24th, at 16:47 Universal Time. Are we in daylight savings time now?
Yes.
I think so. So UT minus 4 hours would be 12. These images were taken at 12:46. Holy shikes. That's pretty recent, right? That's like 10 minutes ago. Isn't that wild? This is what the sun looks like right now. Let's see if we can find one of these images at visible wavelengths. These are in angstroms. So that's 21 nanometers, 13 nanometers. You'll be able to tell when we get into the visible spectrum because the sun will start to look really, really smooth like a ball. Cool. Hey, how about this? We actually have a couple of sunspots today. I was not even expecting that. It's kind of sad. I wish that I could set up my telescope and show you. I did try to do this last year in my apartment. I tried to set up my telescope. It ended up taking too long and I felt kind of bad about it. So I'm not sure that what I got was worth the amount of time I spent setting it up. But it is cool to look at with your own eye. I'm very surprised that we see any sunspots at all. Let's go back 5 years ago. What is it, 2021? Let's go back to like 2016 or something. Let's go to our daily movies. And let's go to 2016, which should have been during a solar maximum, I believe. And let's just pick a damn day. Let's see if we can find that intensity gram that we just saw. Okay, do I know what I'm doing? Do I know what I'm doing here? Let's try this. Huh. What is wrong with me? Well, maybe I picked the wrong day, but I honestly, what I was expecting to see, guys, is I was expecting to see a whole damn bunch of sunspots.
I don't know if this is just like a mislabeling thing, but I noticed on the date next to each of those, it says 2018.
Oh,
So maybe something got mixed up there.
Where do you see that?
Am I just misreading? No, that says 18.
That's last modified, right?
That's what I was wondering. I wasn't sure if I was just.
So I thought that I clicked on 2016, right? Let's go to
You definitely did that.
Let's go to 2015, pick a random month, pick a random day, and let's look at that same. Okay, there we go. Do you see how many sunspots there are there? This was during a solar maximum where you see lots of different sunspots. Kind of cool looking. All right. Anyways, the solar magnetic cycle is actually kind of like, it's a little bit of a mystery of science. We know the sun is doing it, but the actual calculations of the mechanism are a little bit illusory to us. Before I get any more lost in the photosphere, let's learn about the interior layers of the sun as well for completeness. And then I'll see what I can do with the time I have left. Okay. If we go below the photosphere, we're entering layers of the sun that we cannot directly observe. And therefore, if you wanted to be a pesky student and ask good questions, you could say to me, how do you really know what's down there under the photosphere if you haven't seen it and no one else has seen it? And the answer to that question is a little complicated, but it basically boils down to lots of computer modeling. People who are very good at physics, very good at mathematics, and very good at computers, they model using a supercomputer a giant ball of gas. They try to recreate the conditions and the forces and the temperatures just the same as they are in the sun. And they make a simulation and analyze how a ball of gas would behave. Now, to prevent them from just making stuff up, they fact check their models against something called sunquakes, eruptions of bubbles and gas that can be seen at the surface. Another way is through the study of a tiny particle called the neutrino. Neutrinos are generated in nuclear reactions, and they can actually fly all the way through the sun as if it were transparent glass. So we can actually observe the interior of the sun by using neutrino telescopes. Obviously, I've got a lot to say about that, and I don't want to get sidetracked on it. Oh, I did want to show you, now I'm remembering what I wanted to do. One of my former students, was also my tutor, they always constantly update me with cool stuff in astronomy that I might have missed. One of the big hotnesses that I might have told you about before is a spacecraft known as the Parker Solar Probe. And the Parker Solar Probe is currently on a sort of trajectory. It's a spacecraft that's been designed to fly into the outer atmosphere or the corona of the sun. And this is the first time humans have ever tried to do this. I don't know if you guys remember me talking about this, but it launched a few years ago, and it's basically converted itself into a really highly elliptical orbit that's going to travel out past the orbit of Venus or Earth and then plunge in really hard 5 or 6 or 7 times, getting closer and closer to the atmosphere of the sun each time. That's one of our latest science missions. And I don't think it was the Parker Solar Probe, but there was another one that recently produced a super high resolution image of granules on the sun. Let's see if I can find this new image of granules on the sun. It was one of the highest resolution images ever taken of the surface of the sun. And I thought it was, yeah, this is it, guys. And what was just so wild about it is just the detail. Like the detail just looked so creepy. Okay, first of all, this picture, I had never seen a picture like this up until like a year ago. So you have to understand that to see granules and to see sunspots with this level of resolution for the first time, it's like art. Like this is a beautiful abstract painting to me. Like there's so much physics and detail going on here with these cells and bubbles, but they just look so cool. And I actually forgot to show this to my astronomy. That looks like the Eye of Sauron or something. Like it's so wild. And I actually forgot to show this to my astronomy 1020 students. This wasn't with the Parker Solar, sorry. It was the Inouye Solar Telescope on Hawaii. Highest resolution images of the solar surface ever taken before. So I actually need to update my slideshows and get that. Look at that. That's just crazy. Especially when you look at something like this, or you look at that, it makes you realize that just a bunch of, I mean, all it is hydrogen, helium gas, magnetic fields, and light. And yet somehow it looks so beautiful and weird and strange. You know, it's not something you'd be able to predict. Anyways, let's go into the interior of the sun. Let's see where those bubbles are coming from. The inner 3 layers are known as the convection zone, the radiation zone, and lastly, the inner nuclear core of the sun. Taken together, these 3 layers can be thought of as the interior layers of the sun. Just like we can't see the interior of Earth so well, we can't see the interior of the sun. The sun doesn't think of itself as having layers. The sun is just a ball of gas that gets hotter and squeezier as you get towards the center. We, humans, have identified layers of the sun because we've realized that energy is transported through different mechanisms. The physics changes between these layers. Also, the temperature changes. Temperatures for the convection zone, so we're plunging back down into the sun, and temperatures are, actually the photosphere is the coolest layer of the sun, and then we get higher and higher again. The convection zone and the radiation zone are huge, absolutely huge layers. They constitute like 1/3 of the sun's radius each. Let's just look at that, that cartoon again of the interior layers of the sun. Sorry. I don't really like this picture because I don't think it's actually done to scale. I like this one. So the convection zone goes from the bottom of the photosphere, maybe to like just under a third of the sun's radius. And you've got to keep in mind that as you plunge deeper and deeper into the sun, the temperature is constantly rising, the pressure is constantly rising. If you've ever taken a dive to the bottom of one of those Olympic-sized swimming pools, like at a YMCA, if you go to the deep end, it's really hard to get all the way down to the bottom. You can feel the pressure of that water sitting on top of your head. Same thing with the sun. As you delve deeper and deeper, the temperature is constantly going up. There's no one temperature that perfectly describes the convection zone, but I'd say somewhere in the middle of the thing, you'd probably have temperatures as high as 100,000 Kelvin. That is not high enough for fusion. That's not even high enough to completely turn you into a plasma. You have to get up to millions of kelvins before you strip all the electrons off. That happens in the radiation zone. In the radiation zone, you've completely removed every single electron from their parent atoms. And temperatures get to the berserk level of 10 million Kelvin. Once you hit the nuclear core, a key temperature of 15 million Kelvin, that's the temperature at which hydrogen begins to undergo fusion and fuse into helium. Let's quickly look at the way energy is. By the way, at some point in this class, I taught you guys a classic basic science thing, the 3 modes of energy transport. Do you guys remember that? It was a quick little lesson right around the time that we defined temperature. How do you transport energy from point A to point B? For instance, in my glass of delicious ice water, energy is currently flowing from the water into the ice. Sure, Jenna.
Convection, conduction, and radiation.
Right. Today, we got to get into those differences, okay? Because energy is transported by convection in the convection zone and by radiation in the radiation zone. Okay. Let's think about the 3 modes. We could call it energy transport, and because heat is a transfer of energy, sorry, get my screen up there. They also call it the 3 modes of heat transport. They are convection, conduction, and radiation. Okay. Before I tell you what they are, let's see if you guys already know. Can anyone describe in simple, non-fancy terms the differences between these things? It's okay if you can't, but I just want to see what you know. Okay. Well, let's take a peek then. Convection is what happens when hot air rises in a room, say off of one of your household radiators during the winter time. One of my former professors described convection as blobology, okay? The study of blobs. Basically, somewhere down, in fact, actually, you know what the perfect description of convection is? A lava lamp. In a lava lamp, you have 2 different types of paraffin wax, and then you have some kind of a lamp or a heating element down below. The paraffin wax becomes heated through probably conduction or radiation from the lamp. And as the paraffin wax heats up, it expands into a big bubble. The bubble becomes buoyant, like styrofoam in water, because as it expands, its density drops. And then as it becomes buoyant, it rises up to the top of the lamp where it cools off, and then the bubbles contract and it sinks back down. Eventually, you set up a convection cell. And these are happening all around you all the time. A classic example would be, as I was about to mention, a household radiator. Why did they design them with these slats like this? They design them with these metal slats so that you can hold little vertical pockets of air. The air come in contact with the metal heats the air up through conduction, direct contact, and this whole bubble becomes something like a hot air balloon. It begins to expand. As it expands, the gas rises, it displaces cooler air, and cooler air circulates back in, and the cycle repeats itself. The important idea about convection is it is bulk transport. You're transporting big bubbles. So let's write that down. Convection is bulk transport. You transport bazillions of molecules at a time. And it basically means hot bubbles rise, cool bubbles sink. And this is not the only time we're going to be talking about convection in our class. In the convection zone, warm bubbles are heated from below. In the radiation zone, they're irradiated with high energy X-rays and gamma rays, and then they expand, they float up to the top, and once they hit the photosphere, guess what they become?
They would cool off.
Right.
Or light.
They become those things that we call with a special name.
Granule?
Yeah.
That's right. I wanted you guys to make sure that you had the connection that when you see these beautiful images of granules on the sun, let's go back to those really nice pictures. You're basically seeing the bubbles that were bubbling up from the convection zone below. You can literally see those bubbles percolating up to the top. How would I contrast convection to conduction? Conduction is atom to, let's write it down, atom to atom jiggling, okay? Atom to atom, do I know how to spell jiggling? Let me try this. G-I-G-G, jiggling, okay. Atom to atom jiggling, that's how I would describe it. In fact, let's look at a little crappy animation of conduction together. I have one here. If you put a pork chop on a frying pan, the molecules of iron in your cast iron skillet have been heated up. They're still in a solid phase, but they're all violently buzzing and jiggling, kind of like bees in a little honeycomb. You place your pork chop down on the sizzling frying pan, and the jiggling atoms of the pan sear and begin to cook the molecules of meat. And this means it's direct contact. If you pick up a hot spoon that you left in the soup on the stove and that spoon burns your hand, you're getting burned through conduction. You're touching the hot metal. That's different than convection because you're not pushing big blobs of material around. You're touching the hot jiggling molecules that jiggle your molecules, right? Of course, the third method, radiation, that's just light. And we all know that light can heat things up because if you go outside today and stand in the sun, it will feel warmer than when you're standing in the shade. This is something you intuitively know. So radiation is just heating up by light. You know, a fun game to play to test your science knowledge is a little game that I call convection, conduction, or radiation. Think of something that's being heated up or cooling down in your local life and ask yourself, do you know how it's working? For instance, whiskey on the rocks. When you cool down some whiskey with ice cubes, is it convection, conduction, or radiation?
Conduction?
Very good. The cubes are in direct contact with the water. How about if you cook a pizza, like a Trader Joe's, you know, Trader Joe's has those frozen pizzas. I really like the pepperoni one. Try it sometime, it's pretty good. That pepperoni Trader Joe's pizza, when I cook it in the oven, convection, conduction, or radiation?
Convection, right? Because it's the air.
It's actually conduction. Conduction, most ovens, I think my oven is a conduction oven. And that means that I tried to trick you, Ian, and I successfully tricked you. Consider yourself tricked, okay? There are convection ovens. If you ever work in one of those pro pizza shops where they have the big giant ovens, you can tell when they're convection ovens because they'll have a fan and the fan will be blowing bursts of hot air. That's called a that's a convection oven. But most standard crummy little household ovens are conduction ovens, all right?
I even said to myself, I've heard of a convection oven. Maybe I shouldn't say that.
Well, you know, the penalty for being wrong, unfortunately, it's not that I can cut your fingers off or do anything. You know, they stopped me from doing that years ago. So you don't really lose anything by guessing wrong. In fact, you learn something, you win. What if you took a baked potato out of the oven and you put it on the windowsill and you let it cool off? Convection, conduction, or radiation?
Would that one be convection? Well, I mean,
I'm going to be honest with you guys. I'm not 1,000% sure which is the dominant mode of energy transport. In reality, all of those things are actually happening at once. The potato is hot and it's touching the air. The air is a little bit cooler, so there's some direct contact there. There's probably also some steam coming off the baked potato, and that steam is causing a little bit of bubbles rising and falling. I honestly suspect the dominant mode might actually be radiation. That hot potato is probably glowing at infrared wavelengths, and they're traveling through the air. Air is actually kind of a sucky heat transporter. Air is like a good insulator. That's why a sweater helps to keep you warm in the winter. You're trapping little bubbles of air against your skin that keep you warm. It's why a double paned window is efficient for keeping your apartment from losing heat. To be honest, oh yeah,
I have
Nori?
a question, I'm sorry. So I don't know, like, I don't really understand like the point blank differences between the three. Like, if you could just go over it like real quick, like in like super brief.
Sure.
That would be great.
And I appreciate your honesty about that because I'm not sure I'm doing the best job. You know what we should do, Nori, is we should draw a little picture of convection together because I think that will actually help. And it is kind of important, Nori, because not only do we need to understand the nuances for the sun, but you're going to see these same issues coming back when we study the interiors and the atmospheres of planets. Let's draw a little model of a convection cell together. And I don't know if this is going to help, but maybe it will. I'm trying it. Let's draw some air molecules, okay? By just taking some black dots and peppering them around the page here, okay? So let's say these are some air molecules. I'm now going to imagine, and this could be the convection zone inside the sun. I'm going to imagine that somewhere underneath, like in the radiation zone, the radiation zone is a completely ionized plasma. So photons of light, probably in the form of X-rays and UV rays, probably mostly X-rays, honestly, and some gamma rays. Photons are coming up from below and they're heating the gas. But here's the thing. This is a cooler layer of gas at first. So the atoms still have their electrons attached to them and they start blocking the photons and impeding their progress and they start getting heated up. Let's draw a little pocket. And I'm going to use red now. And I'm gonna kind of, actually, I'm doing this the wrong way. I'm going to draw a pocket in which the gas particles have a slightly lower density. And what's happening is this pocket of gas is kind of heating up and it can't transport the energy out through mosh pitting. A mosh pit is conduction, Nori, okay? When atoms are slamming into one another, a mosh pit is conduction. Convection is where you slam into the mosh pit with a, I don't know, dump truck and you scoop all the people up and push them out the door. Okay. Okay. So if suddenly the mosh pit can't release the energy, you start to have this temperature gradient where it's cooler here and warmer there. And honestly, it works just like one of those hot air balloons. This thing expands and it begins to rise. Somewhere higher up, you're going to have a cooler pocket of air. And this pocket of air has become more dense because it shined away all of its light at the photosphere. Here, the light can escape. And this pocket becomes dense and it starts to sink. This is what is known as a convection cell. Big bubble rise, big bubble set. But meanwhile, Nori, conduction can still happen between these atoms. It's just that conduction is not the dominant energy transport mode. You're transporting more joules by big bubbles rising and setting than you are by atoms bumping into each other. I don't know if that helped. It's always hard when you understand something to understand what people don't understand about it. All right.
So I think the key difference, I'm just for myself, the key difference to highlight is that convection is larger.
Larger scale.
Scale, yeah. So more is moving at a time versus
hence the term bulk transport, right, Ian? We're transporting large amounts of atoms at once rather than particles.
Yeah, it was just like a little weird for me trying to figure that out in my head because I was like,
it's hard.
Wouldn't it be convection because it's like the air, but then it's just like the air is hitting it individually. So it was like a weird, yeah, but I got it.
I wonder, Nori, if we typed convection versus conduction, if we would see like a pretty cool picture of them here. I suspect there are really nice photographs. This is a classic science thing. It's honestly just like knowing about life, right? And that's why these cool 101 level classes are great, because you just learn a bunch of basic stuff that teaches you about life. Here they show you different examples. Conduction is taking place when the dummy burns his hand on the handle. We see convection in the boiling water as big bubbles are rising and sinking. Here we see radiation where light is being created in a fire and shining away. By the way, have you guys ever like been around a campfire or a bonfire and you kind of go up towards the fire to roast a marshmallow and suddenly you feel this really intense wall of heat that just comes on you all of a sudden? Do you know what I'm talking about? Do you know what that is? That's infrared photons. You're feeling infrared radiation coming off of the fire and suddenly hitting you, and it's cooking your face like a toaster, all right? So that's an example of radiation.
So,
yep.
From the picture, this is what like I got, and you can correct me if I'm wrong. So like conduction is kind of like almost like contact, like between things. Convection is just like kind of within itself. It's like doing its little thing, you know.
I wouldn't say within itself. I would say it's big bubbles. It's literally just bubbles rising and bubbles sinking. Anytime you see bubbles, convection is probably at work, okay? Except for the magic wand blows soap bubbles. I don't think that's, well,
radiation is just like emitting.
It's just light. It's just light, right? You transport energy by light. If I shine a laser beam at this thing, those are photons. They generate light, or they transport light. Interestingly enough, in outer space, space is a vacuum. There is no convection. There is no conduction. You can only get energy from the sun to planets through photons or radiation. Okay. I have a little bit of time left. Let me see what I can do to help our homework do a little better. I've got 5 minutes left. I want to talk to you about the outer layers of the sun, and I want to talk to you about magnetic fields because I think it's going to help our homework. And I'm going to try to do this really, really quick. So let's go once again to the beautiful YouTube video called Thermonuclear Art. If you haven't seen this yet, Ian, you're going to see me talk about it in Monday's lecture. And these guys can tell you that I went absolutely nuts getting really excited about how cool the sun looks at these different wavelengths. So this is all from the Solar Dynamics Observatory. Let me just find a place that I really like here. Okay. What you are seeing right here is the upper atmosphere of the sun. You're probably looking at the corona, and you can see powerful loops, magnetic field lines poking their way out of the sun. Hot gas is attached to the magnetic field lines, and as the magnetic field lines twist and turn, plasma charged gas particles become excited. You can push gas off the surface of the sun, and you can even create these little eruptions called solar flares, some of which can be absolutely insane. I'd like to show you, if I can find it. There's this video of a massive solar flare. And this video, the first time I saw this, it just blew my damn mind. So I'm hoping it'll do that for you guys. Hold on a sec. I didn't think to look this up. I used to be able to type this in. It's just one particular video that was just really compelling. It was an up-close image of gas. There's just one in particular that I want to show you. And now we have so many good videos. Let's try this. Maybe I won't find the exact one that I wanted to find. Oh, get out of here. Okay. I think it was one of these solar flares, and it was just a close-up view of the sun just spewing gas and plasma up into the atmosphere, and it kind of raining back down. It was absolutely so beautiful. This, of course, is another iconic one, the so-called fiery loops, where you can see magnetic fields just basically pushing a giant waterfall of plasma. Nori, can you tell me what your cat's name is? Again, I like to see kitties in these videos. It helps my day go by better.
Her name is Willow. She just decided to jump up. So
Willow kind of looks like a peanut. It looks like she's black and brown.
she's got like a little something on her face.
Yeah, she's got like a cross. She's like that's like Viking war paint or something. You should have called her Odin. Okay. Anyways, I like Willow. Willow's cute. Keep her in the frame if you can. Okay, how does this work? It turns out that there's an interaction between magnetic fields and plasma. I'm going to try to do this quick bit in 5 minutes. It's not in the book. You can only learn this from me. If I were you, if I were a 1010 student, I might be thinking, what the shit is a magnetic field anyways? I don't even know what the F that means. Let's do a little crash course in magnetic fields. It'll help our homework go by faster. Okay. Call this part of your notes 3 rules for magnetic fields. I, of course, have had the benefit of taking many different classes in electromagnetism. This is a classic branch of physics. You've got to take this course like 4 times at different levels of complexity. And I want to condense the important things I've learned about magnetic fields into 3 rules. Most of your experience with magnetic fields is playing with refrigerator magnets, right? And I'm guessing that you know from refrigerator magnets that magnets have a north pole and a south pole, right? If you try to place north against north, you feel a magnetic field repulsion. If north and south come together, you get the attraction, right? And so that's probably your experience so far. But actually, there's a lot of craziness going on underneath the surface here. The real way that you generate a magnetic field at its most basic is you just take a simple wire and conduct a current of electricity through it. So let's start with how magnetic fields are generated. Moving charges create magnetic fields. And this is the classic picture that you learn about in your electromagnetism class. Now, the moving charges do not have to be in a wire, but a wire is a convenient sort of Example. Your household wires are probably made up of the element copper. Now, copper is an atom that has 29 protons, 29 electrons, and honestly, I don't know what the most common isotope is. Let's just look it up on the damned internet really quick. Copper atom. Oops. Copper atom. What makes copper such a good conductor of electricity? Let's look at it here. This is a great picture. It would be great if it was larger. Okay. Let's see if that works. All right, perfect. So in the nucleus, you have 29 protons and 35 neutrons, and you have 29 electrons. So in theory, your 29 protons and your 29 electrons should cancel each other out, and you have absolutely no net charge. And that's kind of true. But here's the real true. The real true is that the first 28 electrons are so perfectly filled in their orbiting shells that they actually do a really good job in shielding the last electron from the inner nucleus. In other words, even though this is only 28 electrons, they have so effectively blocked the positive charge that your very last electron, the so-called valence electron, is in a kind of casual, non-committal relationship with the atom. It's kind of doing it, but it doesn't know if it really cares. And all it takes is a little bit of pressure. All you got to do is just introduce some other electron into the picture, and this guy will go boop, and it will pop right off and flow to the next atom, okay? The valence electrons are just dangling at the edge of the atom, and they can easily be pushed off. This is how you conduct electricity. So what we're going to do is we're going to send a little current of electrons flowing through those copper atoms, and they're going to flow through this wire. And as soon as the charges begin to move, magic happens. A magnetic field is created that surrounds that wire in a kind of circular loop, almost like a paper towel tube, okay? The magnetic field lines circulate around the negative charges. That's how you generate a magnetic field. And then you can do some kind of fun things with it. Let's look at my slides real quick. Slide 5. Okay. So I don't have time to get into the horseshoe magnet. That's a little more complex, but you send a current down a wire, you generate a magnetic field. Now imagine I attached a thin wire to a 9-volt battery or something, and then I took a pair of needle nose pliers, and then I bent the wire into a circular loop. As the current flowed in a circle, the magnetic tube would take the form of a pair of bunny ears, and these bunny ears are what are known as a dipole magnetic field. Dipole magnetic fields are found everywhere. We usually associate this side with the North Pole and this side with the South Pole. Not only do we see dipole magnetic fields in circuits, but actually the Earth itself famously generates a dipole magnetic field. What does that say to me? It says that somewhere down in the belly of Earth, there is a big layer of liquid, hot, glowing metal. Charges have been ripped off of the metal, and as Earth rotates every 24 hours, you're sloshing around that charged liquid metal, and boom, it's the same thing as putting a current in a circle. You know, the sun would like to generate a dipole magnetic field as well. But here's something weird about the sun. The sun is not a solid ball like Earth. It's a goopy ball of gas. And the sun does not have to rotate all at the same rate, nor does it. Famously, the sun undergoes differential rotation. The equator of the sun rotates faster than the poles, and this drags the plasma and the magnetic fields around and around and around until they become super twisted. Let's take the last two things, and then we'll take a little tea break. Let's take our last two rules for magnetic fields. Okay, second rule is this. other charges stick to, or you could say they gyrate around magnetic fields. So what happens is if you have a magnetic field line poking out of the sun, and you send, for instance, a high-speed proton towards it, when the proton hits the magnetic field, it'll sort of oscillate and gyrate around the magnetic field, and the charges become stuck to the magnetic field lines. And actually, that should make a lot of good sense to you. I don't know about you guys, but I can't see any magnetic field here. Can you? Magnetic fields are invisible. And yet, Jenna, when I showed you that video of the sun here, you can see the magnetic fields, right? Why is it that you can see the magnetic fields here? Because plasma is getting stuck to those magnetic field lines. And when the protons stick to the magnetic field lines, they emit high energy short wavelength X-rays. I'm running out of time for our lecture. So normally I have a speech about how the X-rays are generated, but when charged particles strike magnetic field lines, the plasma will stick to the magnetic fields and they emit X-rays. This is how we can see the magnetic fields in the corona, by looking at X-ray wavelengths. Our third and final rule, and then we'll end our lecture, is that just as charged particles can stick to magnetic fields can stick to big blobs of charged particles. Magnetic fields stick to, and they get twisted by bulk charges, which is basically just another way of saying plasma. Plasma can bend and twist magnetic fields. You can see the dynamic interaction in all of those beautiful videos that I showed you. For instance, in the fiery loops, notice that gravity is pulling the plasma back down to the sun, but the plasma is constrained to move along the magnetic field lines like beads that are sliding along a wire, right? You can also see that in the other videos, like in the thermonuclear art videos, you can see those magnetic fields winding and twisting as the bubbling gas that's swirling around in the sun is pushing and distorting those magnetic field lines. These magnetic storms can be very violent, and they can cause huge bursts and eruptions from the surface of the sun. Sometimes they're called solar flares. That's when they erupt and get sucked back down again. But during a coronal mass ejection, the sun will actually belch a huge, oh, did you see that solar flare over there? That was, did you guys see that? That was nuts. That actually might have been considered a coronal mass ejection. When it actually blows material right off the sun, it's called a coronal mass ejection. Do you know that in 1980 something, the sun had an emission of a coronal mass ejection that was so powerful, it sent a burst of charged particles that struck some power grid in Canada and knocked out half of Canada's electricity for a day and a half. Canada actually had a day and a half blackout because of some really massive burst of charged particles from the sun. So this stuff can actually affect Earth in extreme circumstances. Anyways, if you get some downtime, please watch this whole video. If no other reason, it's just freaking beautiful and wild and cool. And I enjoy showing it to my friends. It usually blows their mind. Okay, we've wasted another hour and a half talking about eruptions of the surface of the sun. I don't know why we did that. Oh, I'm sorry, I went a little bit over here. Let's take a 15-minute break, and then we're gonna hit that homework. Does that sound good? All right, sorry about going over, guys. I got a little carried away. It's 1:40. At 1:55 or so, we'll start the homework. Deal? All right. Now, you're all gonna participate with me, right? Because I do have this pre-recorded, but I'm down to do it live if you're down to do it with me. You understand what I'm saying? All right, okay. All right, so I'll see you guys in 15. Hi, Painful as it is, we have to get back to work. You guys ready to do this chapter 14 stuff? Let's hit it. Let's see if we can punch it out real fast. Today's session is, what is it? Is it homework 6 we're on now? If you guys can call up those questions, that will speed this whole thing up a lot so that you're ready.
No, it's homework 7.
Oh, I'm sorry. Right?
I think I have it up now.
Okay, will you, hold on, let me do the usual format and setup for you guys, okay?
I actually have a quick question.
Hit me, Nori.
So I watched the pre-recorded Monday lecture because I can't make it on Mondays. But you gave us, it said lecture 8, but the homework or like the lab said 7.
Yep.
I just wanted to, because I have this problem where I submit it in the wrong thing, and I think we're all kind of acquainted with that.
Yeah.
I wanted to make sure that I'm submitting this next one to 8, is it? Or is it 7?
So do you mean the homework or the lab?
The lab and the homework. Or are
So
they off?
The homework that we're about to do is right here, homework number 7, okay?
Mm-hmm.
So you should submit today's work to homework number 7.
Okay.
The lab was lenses and telescopes. And since I showed you guys the AS1020 version, since we didn't do it last semester, each semester has like little nuances and variations. So 1010, your class this year did lenses and telescopes, and that was also lab 7, okay?
Okay, so they're both gonna be submitted under 7 today.
Right.
Like if I go to submit that.
No, well, hold on. I don't like it when you say it that way. Monday's lab was lab 7, lenses and telescopes.
Yeah. Mm-hmm.
Today, Wednesday's homework is homework.
Yeah, it's also 7. Okay,
Right.
Yeah, that's what I meant.
And remember to watch the lab in case you have not done it yet, but it sounds like you have.
Oh, I did.
The lab was here at timestamp 1:30. All right, okay, good. So let's write down our name. And that might have been helpful for other people later on watching this, so that's a good question, Lori. We have AS1010, our class. Don't forget to put your section, whatever the hell that is. This is homework number 7. Sorry that I was confusing at the beginning. The problem numbers are from chapter 14. What do we got, Ian?
50, 55, 56, 59, and 62.
All right. Ian, you're up. Chapter 14, number 50. What do we got?
All right. Number 50 says solar energy output. Observations over the past century show that the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more. Explain why changes in X-ray output can be so much larger than those in the output of visible light.
Okay. To help you understand this question, I need to first test your knowledge about the sun. Class, what does the sun put out more of? Visible light or X-rays?
I would guess X-rays. No.
I would guess visible light.
Why would you guess visible light, Jenna?
Because I guess just purely like simply because it's so visible, because we can see it. So
Well, remember,
so
yeah,
big.
but just because you can see it doesn't mean, oh, how do I put this? Yes, it's so visible and we can see it. The real issue, Jenna, is if you look at the spectrum of the sun. Remember that during our spectroscopy lab, I showed you the spectrum of the sun. I held up the spectroscope to the window and showed you some white cloud, right? And the spectrum of the sun, I have it here in this slideshow. When I showed you the solar spectrum, it was actually an absorption line spectrum, meaning you saw a rainbow, but buried in the rainbow were some faint absorption lines. If you make a plot of the intensity of sunlight as a function of wavelength, you get this graph here. This graph shows us the spectrum of the sun, and it compares the actual spectrum of the sun to an idealized blackbody at 5800 Kelvin. What you're seeing is that there's super good agreement between the spectrum of the sun and an ideal blackbody. The sun is emitting light at all wavelengths, just like any other blackbody. And just like any other blackbody, there's usually one wavelength that it emits more than others, the peak wavelength, which is described by Wien's law. Okay, let's just look at this. This is brightness on this axis. This is how much light is coming off the sun. And this is wavelength. First, why don't you guys show me where's the visible light portion of the spectrum on this graph?
It's around the peak because it's between like 400 and 800, right?
So another 400 to 700. So you can already see, Ian, that the sun's giving off way more visible light than any other type of light. Correct, Ian? That's the point. Is the sun ultimately is a black body. Where would X-rays be on this graph? No? No one knows that question?
It's
Yeah.
below. It's below ultraviolet, so it's towards the start.
Like down here, right?
Mhm.
So how would you say the flux in visible light compares to the flux of X-ray light from the sun?
Visible light is much higher.
Right, right. So wait a minute, then I'm confused, Ian. What the hell is this question actually asking?
So let me just read over it again for myself.
I thought it was saying, why do I get 10 times more X-rays from the sun? But now I realize it's not actually asking me that, is it?
Yeah, it's just saying it gets multiplied by 10. So just because
Wait,
it's
what gets multiplied by 10?
the X-ray output, yeah. It says its X-ray output can vary by a factor of 10 or more.
So in other words,
well, so you're saying that's not the minuscule amount of X-rays it's putting out. It's not multiplying that by 10.
This is just about reading comprehension to make sure you understand the question before we attempt to answer it.
Okay.
What is the question really asking us? You might actually already understand it. I might be making this pointlessly complicated.
Okay.
It's not that the sun's giving off 10 times more X-rays. It's that the X-rays that it does give off are 10 times more variable.
Oh, okay.
Yeah, I was worried that might. Let's draw a graph of this. Okay, we need to draw a graph. Okay, we're going to draw a graph of the brightness of the sun as a function of time, and this graph will explain what the question is asking. I want this as part of your answer, so put this on your page. On the y-axis, we're going to plot the brightness of the sun in, say, watts per square meter. That's the quantity of light. And on the x-axis, we're here going to plot time in years from the year 1900 to today, 2020. I know it's 2021, but who cares? A little over 100 years, right? I'm going to plot the visible light using black. And what you see is the sun's going to give off a lot of visible light, but it's going to stay very steady for the most part. So here I am showing the visible light, and the visible light only has an up and down fluctuation of 1% at best. Now I'm going to plot the X-rays in blue, Notice my symbolic use of colors, by the way, since we're on the blue end of the spectrum. And I'm plotting less X-rays than visible light, but they're much more variable or fluctuating. So what we see is an oscillation where you get big spikes of X-rays and then quieter periods with less X-rays. The idea being that the maximum X-ray output is a factor of 10 times greater than the minimum output. By the way, I don't like this jazz. I don't like comparing a factor of 10 to 1%. They should both be in decimal form or they should both be in percent form. Who knows what the number 10 is expressed as a percent?
0.1.
False.
Percent. No.
The number 10, that you're thinking of 10%. I'm talking about a factor of 10, not 10%. What I mean by a factor is the raw number 10 itself. Okay, let's try a simpler question. The raw number 1, if you express it as a percentage, what does 1 mean?
1%?
Pardon?
Is it 1%?
Jesus Christ, guys. I hope I'm
be
never at a restaurant with you guys trying to figure out the bill, or we're all
Be
1 over
screwed.
100?
100%, right? And then
The number 1 is a 100%, right? So what would a
Yeah.
factor of 10 be?
1,000.
1,000.
1,000%.
This is better because now we're all expressing. So you can see that the X-rays compared to visible light fluctuate 1,000 times more than the visible light. This is what the question is asking, Ian. Why are the X-rays so fluctuating when the visible light is so steady? What do you think the answer is?
I am not sure where to start thinking about this.
Kim, Nori, Jenna, if you had to take a guess. Could any of you guess why X-rays are? Why don't we look at a picture of the sun at X-rays, and let's look at a picture of the sun at visible light, and let's see if that gives us any inspiration. Video 3 is a video of the sun at visible wavelengths. Okay. Now, let's look at a video of the sun at X-ray wavelengths. I'm getting the sense that that didn't help too much.
Is it because there are like sort of like bursts of like those waterfalls?
Yeah, I was.
They rise and fall because like there's like different like.
They're actually, the magnetic fields heat up the plasma and they cause X-rays to be emitted, right? The reason why you could see the magnetic fields in those videos, Nori, is because the magnetic fields in plasma interacts to release X-rays. In fact, I know no one actually reads the book, and I know no one is ever going to read the book ever again, as long as I teach this course. So just this once, I'm going to read you a little passage from the book as if we were the sorts of students to do that, okay? And I'm going over to page 481, and I'm just going to read a single sentence under the heading of solar storms. In fact, as part of my dramatic reading, let's see if I can autofocus this so you guys can read along with me. Can I read this backwards? I've never tried that before. Solar storms. The magnetic fields winding through the sunspots and prominences sometimes undergo dramatic and sudden change, producing short-lived but intense storms on the sun. The most dramatic of these storms are solar flares, which emit bursts of ultraviolet light and X-rays along with charged particles into space, moving at nearly the speed of light. So according to that passage, The origin of these X-ray fluctuations is, take it away, class,
Magnetic fields.
the changing and variable magnetic storms. Exactly. So let's see if we can put this into a paragraph form, and I'm going to flush out even a little more detail. Please include this little graph and this paragraph that we're about to write as part of your answer. And we're really going to try to get into it here. X-ray emission from the sun is so much more variable than visible light emission because the X-rays are produced in different layers. Sorry, I don't know if, let me try to get a little closer here. The X-rays are, I bet you guys can't read that. The X-rays are produced at different layers and by different processes. And now we're going to explain those layers and processes for X-rays versus variable light. This is the big idea. Now we want to get into the weeds a little bit. X-rays are produced in the sun's, okay, let's see if you can do this, guys. What layer of the sun primarily produces X-rays?
The photosphere.
False.
Okay.
In fact.
Oh, would it? No. Hold on, guess.
Go ahead, Ian. Try again.
I was gonna say chromosphere.
No, not the chromosphere. I didn't quite finish this calculation. This is a picture, a video of the sun at X-ray wavelengths. Once again, Ian, notice that the photosphere down below is actually black. The photosphere is dark because it doesn't produce any of the X-rays. X-rays are all being produced up here. This is not the chromosphere. This is the corona, the outermost and hottest layer. Okay? I kind of didn't fully explain that in today's class. There were little bits that I had to omit, and that sadly was one of them.
So,
oh yeah?
Sorry, if you don't mind me asking. So what, I wasn't really clear on this. I don't know if maybe you covered it on Monday, and I'm going to find out later today, but like, what is the, is there like a, what defines the difference between the chromosphere and the corona? So I was under the impression the corona was further out.
They're both the atmosphere. It's just how high up and how hot they are. In fact,
yeah.
I actually did a bad job here on this today. I was so busy trying to get through all the layers of the sun. Here's a picture of the corona. The corona mostly gives off X-rays, but it's so stupid hot at 1 million Kelvin that it actually gives off visible light. You can actually see the corona during a total solar eclipse. When the photosphere of the sun is blocked out, notice how far out this extends, Ian, maybe 1 or 2 solar diameters, right? Because it's at 1 million Kelvin, this is also giving off X-ray light. The chromosphere is a little cooler and it sits underneath. The difference really is just in the temperature. Because this is more like 10,000 Kelvin, it tends to give off more ultraviolet light than X-rays. So you look at, so when you look at X-rays, you see the corona. When you look at ultraviolet light, you see the chromosphere.
Got it. Thank you.
All right. So they're produced at the sun's corona. X-rays are produced in the sun's corona when charged particles interact with magnetic field lines. Their charged particles are interacting with magnetic field lines. As the magnetic storms fluctuate with the sun's 11-year, and here's an important concept, the 11-year solar magnetic cycle. As the magnetic field storms fluctuate with the sun's 11-year solar magnetic cycle, so does the X-ray emission fluctuate. So that kind of explains the variability in the X-rays. Let's see if we can explain the variability in the visible light now. Produced in the sun's corona, charged part. I'm just reading this to make sure I've included everything. Visible light, on the other hand, is produced at the sun's, okay class, what layer produces the visible light?
That's the photosphere.
Yes. Guys, can I erase some stuff up here? All right. I'm running out of space. Visible light, on the other hand, is produced at the sun's photosphere by what physical process produces light at the photosphere?
Thermal blackbody radiation.
Excellent. Exactly. By thermal blackbody radiation. You guys are starting to get good. See, now you're actually becoming interesting to talk to because you know things like this. By thermal blackbody radiation, as the sun's temperature I said the sun's temperature, but I should say the photosphere's temperature. As the photosphere's temperature remains constant at 5800 Kelvin, so does the visible light remain constant. With only a 1% fluctuation due to blank. Class, what do you suppose is causing the 1% fluctuation in the visible light output of the sun? What could possibly be causing a tiny change?
Sunspots?
Exactly. These dip a tiny little bit of the sun's light during the solar magnetic cycle. Nicely done. Get all that down and we'll move on. You guys are pretty quick. So Jenna, let me know when you're ready to proceed. Or if someone's still writing, shout at me. Jenna's good to go. I'm going to erase unless anyone would like to object. All right. Nori, you feel good about reading something for us?
Okay.
Chapter 1455.
So the question is chemical burning and the sun. When an object burns in a fire, the amount of energy released through this chemical burning is typically about 10 to the 8th power joules per kilogram of mass burned. Use this fact to estimate how long the sun would last if its energy source were a huge fire releasing chemical energy rather than its actual source fusion energy.
Okay. So in other words, let's imagine that the sun is a big ball of burning logs, okay? So let's draw a log. It's big, it's heavy, it's wood, okay? And now we're going to imagine that the sun is a big ball of fire. Here are some dancing flames, the best of my ability, okay? And these burning logs, well, we know some things about the sun. We know that the light output of the sun has a luminosity of 4 times 10 to the 26 watts. And we know that the total mass of the burning logs needs to be the same as that of the sun, 2 times 10 to the 30 kilograms. So this is one hell of a bonfire. This is the energy that is released in the form of light. You burn 10 to the power of 8 joules, or you release 10 to the power of 8 joules of light for every kilogram of log. And the name of the game is to figure out how long can the sun shine. We talked about this in our lecture today. Do you guys have any idea how to start this problem or to go about it, given these 3 quantities? I'm going to teach you guys a new skill here today, but before I teach you, I need to know what you're capable of. Would any of you have any idea how to go about doing this?
Would you use the ideal gas law? Or does
Good
that not
thought.
apply?
No, here you wouldn't. Because here you're just talking about a big stack of burning logs. You know that the energy is, we're telling you for each kilogram of log how many joules of energy come out. Why don't we start this way? Whoever said that, I'm sorry, I lost track of you. What kind of units should our final answer have? I want you to think about this in a different way. What should our units be?
Would it be years because it's asking how long?
It could be years. It's probably some unit of time. So years would be an example. I want to teach you guys another variation on dimensional analysis. I like to think of it as dimensional analysis level 2 for semi-pros, okay? Sometimes you can figure out how to solve a problem by looking at the units of all the numbers that you have to work with, and then figuring out what units you want to end up with, and then just jiggling them around until the units cancel out correctly. For instance, we have 1, 2, 3 numbers, so I'm going to make 3 division bars. 1, 2, 3. And at the end, I want to end up with some kind of units of time. Someone suggested years. but they don't necessarily have to be years. They just have to be a unit of time. Your job, class, and I want to see who can do this, is to tell me how to place the numbers into the slots in such a way where everything cancels except for some unit of time. Now, right now, I don't see any units of time up there, or do I? Where are the units of time hiding? Ryan in the background says in the watts, and you are correct, Ryan. Ryan, but how are they hiding in the watts? What's a watt? Nope, it's not 1 per second squared, unfortunately. But now that you've got the class on the right track, Ryan, maybe they can help us get there. Ryan's on the right track. He just doesn't know what a watt is.
Is it, I have it written down as 1 joule per second.
That's right. A watt is a joule per second. Now that I see that of my 3 numbers, only 1 number involves time, and that's the light output. And I'm now going to realize that I probably can't get years out at first, but I could potentially get a time in seconds. Okay, class, someone take it away. Tell me where to put the numbers. Actually, tell me where to put the units such that I end up only with seconds. This is dimensional analysis level 2. By the way, this is also how professional scientists solve problems. You can solve many problems this way. Any thoughts?
This
getting
might be
distracted
wrong, but I figured I'd give it a try.
Okay, give it a try.
Well, since we want seconds as the final answer, I might put seconds on the top on the
Sounds like a good
right.
idea to me. And then what?
And then put joules on the bottom.
Right. Those two things are connected to each other.
Yes.
We can worry about the numbers later. Let's say you've got seconds per joule. What else? We got to get rid of those joules.
You could put joules on the top of the next one.
Uh-huh.
And kilograms on the bottom.
Beautiful. I like your smooth dimensional analysis moves. We've now killed the joules, but we still have pesky kilograms to manage.
So there's no other unit with the last one, so just kilograms on the top, I guess.
Correct. Because that number just has a kilogram. Okay, now you've done this just right, Ian. Tell me how to put the numbers in to make this cool.
Okay, so you would put 4 times 10 to the 26th on the top of that one, the far left with seconds. Or no, on the bottom, I'm sorry.
You have
I meant
4 times 10 to the 26 joules
yeah.
per second, right? So it's
I meant that. I just was looking at it as joules over second next to the unit.
now it's seconds per joule. You got it upside down. So 1 second emits 4 times 10 to the 26 joules. How about over here?
There, that would be 10 to the 8th joules on top, and then 1 on the bottom.
Yeah, I'm gonna have to ask you guys to be careful here because I've seen this thing happen before. I don't trust you guys to write 10 to the 8 joules because y'all gonna do stupid stuff on your calculator like this. You're gonna type 10 exp8, which is a classic rookie move. 10 exp8 means 10 times 10 to the 8 or 10 to the power of 9. You should probably write out 1 times 10 to the 8. I don't know if you're ready to handle that kind of thing yet. Okay. How about this last slot?
Just 2 times 10 to the 30th on the top.
This is exactly how to do it. Congratulations. You've now learned dimensional analysis level 2. You can solve so many problems this way. Punch them up. Give me an answer. Punching is a you job. Okay. 1 sig fig is fine.
I got 5 times 10 to the 11th seconds.
I love it. Jenna, that's our final answer. But someone pointed out earlier that it would be a lot cooler to know how many years the sun could shine as a big pile of burning logs. I need us to convert seconds into years. Do you guys know the number of seconds in 1 year? Did I ever give you that conversion factor? I'm kind of tempted to, just to speed things up. Hold on just a second, guys.
If you did, I definitely don't have it.
Could you possibly do the calculation on the calculator? Because I did it and it came out like 8 to the something's power. So
Okay,
I just don't want
in the interest of time, because there's other things we all want to do today, I'm just going to tell you the number of seconds in 1 year. I believe that you guys could work this out if you had to. So I'm going to do this for you. 5 times 10 to the 11 seconds. The conversion factor, which is really useful for all kinds of things in astronomy, is 1 year is pretty close to pi times 10 to the 7 seconds. So 1 year is 3.15 times 10 to the 7 seconds. I know that's not exactly pi, but that's the joke that we use to remember it. Okay, so punch them up. Tell me how many years that is. Hold on. Okay.
I got 16,000 years about.
16,000 years. And this is why the sun could not be a big pile of burning logs, because it would burn itself out in less time than there was between us and Brontosaurus, right? Dinosaurs went extinct 65 million years ago. Presumably the sun was still shining then. Nicely done. By the way, the real takeaway of this problem, it's not just that the sun's not a ball of fire. That's a powerful technique. You don't have to just save this for your astronomy class, guys. You can solve problems in all kinds of other courses that you take with this skill. Don't forget it. 2 down, 3 to go. Kim, would you like to read us number 56? Oh.
Sorry, I had to unmute myself.
That's okay. Hey, Kim, and can I erase this?
Yep.
All right.
I'm all set.
All right. So let's get that number 56 going, Kim.
Okay. It's the lifetime of the sun.
Okay.
The sun's chemical composition was about 70% hydrogen when it formed, and about 13% of this hydrogen was available for eventual fusion in the core. The rest remains in layers of the sun where the temperature is currently too low for fusion. A is use the data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun.
So we're going to use this. We're going to use the mass of the sun, and we want to find the mass of fusion. Just for kicks and giggles, let's draw a symbolic picture of what's going on so we can visualize the problem. This ball represents the sun. Now, I know 70% is not exactly 3/4, but let's face it, 70% is close to 3/4. So it's kind of like if I put a bunch of dots that represent hydrogen, this quarter of the sun, roughly 1/4, is represented by helium. I'll make bigger dots for the helium because helium is 4 times as massive as the hydrogen, right? And we know that helium cannot fuse. We know that in the sun, hydrogen fuses into helium. So if you're helium, you're already used up. You already used up fuel. You can't make any fusion from that. So a good 30% or a quarter of the sun is not available for fusion. The rest of the sun is hydrogen, but the problem is most of that hydrogen is not hot enough. The stuff that is hot enough is whatever fraction that hydrogen is there, that's also in the core where temperatures are high enough for fusion to proceed. In other words, we're trying to find the mass of them red dots, the ones that are not helium, that are hydrogen, but also in the 13% core. So what should I do?
I know it's so we want to find out what the core is.
The mass
And
of
the core.
The mass of the core available for fusion. We want to find the mass of the hydrogen in the core. That's how I would put it.
Okay.
It's actually a pretty simple problem.
Looking at it, I would say 2 to the 10 to the power 10 of the 30th times the 13%.
Yep. That'll give you this whole circle, but we also have to consider only the hydrogen. So we multiply it by 13%, but
Well,
we have.
go ahead.
No, go ahead. When we do the same thing with the hydrogen at 70%.
right. So this is like a compound percentage. You could do it in either direction. I would have taken all of the mass, multiply it by 70%, which reduces it to only the hydrogen. Then I'd multiply by 13%, which is only the core. It doesn't matter which direction you do it because of the associative law of multiplication. So let's just do that. So the mass available for fusion is 2 times 10 to the 30 kilograms. How do we represent 70% as a decimal? Ian?
You said 70%? That would be 0.7.
0.7, good. I picked on you because earlier we had that issue.
Yeah.
And then we're going to multiply by 13%. All good in the hood? All right, why don't you guys do that up and tell me what you get?
I got 1.82 times 10 to the 29th, or 2. Sorry.
Hey, can you guys just give me 1 sec? Just 1 sec. Little kerfuffle. Hi, guys. Sorry about that. Did you get a number? I'm curious what you guys were you trying to solve the problem?
No, I was just asking about something before.
Oh.
Like to do the calculation because I got it wrong for the previous question.
Oh.
So I just didn't want to
Sure. I wish you had told me. So let's do it together, right?
Mm-hmm.
From the previous question, it was 1 EXP8. I'm doing the middle one first.
Mm-hmm.
Times 2 EXP30.
Mm-hmm.
Divide by 4 E26,
Mm-hmm.
right? No, yeah, that's right. 5 times 10 to the 11.
Yep.
Is that the part you were struggling with?
Yeah, because it came out like 8 point something, so I just didn't want to
You probably might have gotten messed up in your order of operations. You could have gone 1 divided by 4 EXP26 times 1 EXP8 times 2 EXP30. I'm not sure what you did do, but can you do it this way from now on?
Yeah.
All right, cool. Anyways, what did you guys get over here for the massive fusion?
How many sig figs? I got 2 times 10 to the 29th.
That's fine.
Okay.
Yeah. Hold on a second. What was it to 2 sig?
Or 1.8.
Let's go with that for fun. So you get 1.8 to times 10 to the 29 kilograms. Is that what you got? All right. What's part B ask, Kim?
B is the sun fuses about 600 billion kilograms of hydrogen each second. Based
I'm sorry.
on your result.
That little kerfuffle I just had, I have a guest who's like trying to, she is parked in a garage and I just have to, can you just give me one more second? I'm worried she's going to get stuck in there because she doesn't know the I just realized she was going to get into the garage and it's not very obvious how to get out of that thing. So I apologize. Don't even want getting trapped in parking garages today. Okay, so I'm sorry, Kim, can we try that again?
Yep. The sun fuses about 600 billion kilograms of hydrogen each second. Based on your result from part A, calculate how long the sun's initial supply of hydrogen can last. Give your answer in both seconds and years.
Okay, let's try that same method we did last problem, dimensional analysis level 2. We have a mass available for fusion. We have a fusion rate, and we want to know how long can it last. Kim, can you tell me how to do this? If I have a mass in kilograms.
Yep.
Yep, what do I do?
We're going to time the fusion rate of 600 of 10 to the 9th kilogram seconds times the 1.8 times 10, the 29 kilograms.
Okay, let's look at that from the point of view of units. Kim, I like your dog. Your dog's going nuts in the back.
Yeah, somebody's in the hall going up the stairs.
Gotta love home teaching, right? We're all distracted.
Oh, sorry.
Kim, if I multiply kilograms per second times kilograms, what will my final units be?
It'll be kilograms squared per second.
So that doesn't actually give me a length of time. Why don't you try again?
So we're going to do the kilograms second, and the other one's going to be the kilograms is going to be on the bottom.
Okay, if I do that, Kim, then yes, my kilograms will cancel. But that final unit is not seconds because it's on the bottom. Seconds on the bottom is per seconds. That is not the same as seconds. So try again. Keep trying until we get it.
Well, it says per second. That's why I was.
Right, I know.
Okay.
The fusion rate is per second, but how long is not per second? How long is seconds? Does that make any sense?
It makes sense, but I'm trying to figure out.
What other way could you flip this stuff around so that you ended up with only seconds and they were on the top instead of the bottom?
You would have to do seconds on the top and kilograms on the bottom.
Very good. And then?
And then it would be kilograms on the top.
Yes. Good. Now help me put in the numbers.
Okay, so
tell me what to put in.
2 to the 10th times 10 to the 30th on the top.
No, we're only working.
Oh, I'm sorry. Yep. 1.8 times 10 to the 29th.
Where does that go? In which slot?
The bottom.
Hold on. This is your kilograms per second. This is your kilograms.
Oh, sorry. I was looking at 1 point. So that would go on the top over here, on the top, on the second side. 1.8 times 10 to the 29th.
That's right. That would go over here. And what would go over here?
Would be 600 times 10 to the 9th.
On the top?
That's kilograms per second. So that's.
Yeah. What? Let me erase it.
Okay.
Yeah. What this means, another way to look at it is 600 billion kilograms per 1 second, right?
Okay. So one on the top, and it'd be the 600 times 10 to the 9th.
That's right. I needed to make sure that you understood. Once it's still kilograms per second, but you're flipping it upside down.
Yep.
So you can flip the number with it, okay?
Mm-hmm.
Okay, in other words, Kim, it looks like all you really are supposed to do is take the mass and divide it by the rate, and that will give you an answer in seconds. So
Yep.
Go ahead and do that. What do you get?
Three times 10 to the 16th seconds.
Very good. Let's convert that to years. What's my conversion factor?
Is 3.15 times 10 to the 7th seconds.
Is 1 year, right?
Yes.
So punch that up. Tell me what you get.
Three. I got 7. Hang on.
No
Did I
bloody
just-
way. 16
Yeah, no.
minus 7 cannot be 0, right?
Divided by 3.15 exponent 7.
Hold on, I want Kim to do this because Kim's scared.
9.
Yep.
Yeah, let's see, 9. What is it? 3, 6, 7, 8. 9 times 10 to the 7th.
Is it just 9? What's your second sig fig?
5. So if it's
Count better.
round it.
Kim, you got to count better. You got to count better. Look, Kim, I'm going to do the same thing that you just did. I'm worried that you have the right answer, but you're not reading it right. And that's something we definitely got to straighten out. Okay. 3E16 divided by 3.15 EXP7. This should be pretty simple. Okay.
Yeah.
What's your lead digit?
9.
But we're going to keep the 0.5, okay?
Okay.
But you need to count better. 9.5 times 10 to the what?
7th.
All right. Kim, your decimal place
I've-
is there. Will you count with me?
Yep.
1, 2, 3, 4, 5, 6, 7,
8. 8.
All right, someone fucked up somewhere. Okay. That's not the right answer. I know. I think it's the 3 times 10 to the.
yeah.
What happened, Jenna?
I was gonna say that.
Oh, sorry, my internet's a little.
What?
The first part, the second is 3 times 10 to the 17th, not the 16th
bloody
seconds.
hell.
So I think
Who
that makes a
did-
difference.
Kim, did you do that?
Oh, it's frozen.
Oh, I'm not frozen.
Sorry.
Yeah.
All right. Kim, you're in the doghouse. Did you give me the 16?
I must have.
Well, I don't know.
I don't have it written down because I was typing it.
Oh. What was it supposed to be, Jenna?
3 times 10 to the 17th seconds.
All right. Hey, look, if that happens again, if you see something you don't agree with, the reason we're all supposed to punch is to fact check each other. Jenna, Ian, don't be silent when that happens because I'm
Yeah.
not punching, so I don't remember if it's 16 or 17 every time. Okay, let's try that again. Kim, my friend, convert that to years and tell me what you got.
So 9.5 times 10 to the 9th
Units?
year.
Good. Okay, Kim, get all this down because I'm going to need to erase it.
Yeah.
Up here, I'm going to do part C. shucks.
600.
Val? Tim, when you're ready, can you read this part C for us?
Yep, hang on 1 second.
Ugh. Feels like this homework lasts 3 times 10 to the 17 seconds.
I know. 5, 7 equals 9.5 times 10 to the 9th years. Okay. Okay. Part C is, given that our solar system is now about 4.6 billion years old, when will we need to worry about the sun running out of hydrogen for fusion?
So we have a total lifetime of the sun of 9.5 billion years. We're going to subtract the current age of the solar system, 4.6 billion years, and that's going to tell you how long we have left to live on Earth.
4.9 billion.
Nice. Just like we mentioned in lecture today. This calculation is the calculation that shows us that the sun has 5 billion years left to live. $56 down. 59 is pretty simple from what I remember. Jenna, I'm going to have you read the last two since there's only 4 of you. Yeah, Jenna?
Yep. Okay. 59. The color of the sun.
I'm sorry, Jenna, just give me a sec here.
Mm-hmm.
All right, hit us.
Use Wien's law and the sun's average surface temperature of about 5,800 Kelvin to calculate the wavelength of peak thermal emission from the sun.
Wien's law tells us that the lambda max, that peak, remember Ian, when we looked at the black body spectrum of the sun and we saw that it peaked right in the visible? All right. Well, that peak can be calculated from this formula. 3 million nanometer kelvins divided by the temperature. This problem is super easy and yet, shall we say, illuminating. Let's punch in our 3 million nanometer kelvins and divide it by the surface temperature of the photosphere, 5,800 Kelvin. What do you get?
$517.
Let's make it 520. I still need some units on there, Jenna.
Nanometers.
What color or regime of the electromagnetic spectrum is this?
Red.
False.
Orange.
False.
Oh, is it green?
Yeah. Let's just look at the visible spectrum really quick. So this is a visible light photon. Humana. See that? 520 is as green as the day is long, okay? Fine. What were the other two parts of the question, Jenna?
What color does this wavelength correspond to the visible light spectrum? Why do you think the sun appears white or yellow to our eyes?
Okay,
I think we kind of
take issue with the way they wrote that. There are completely different explanations for why the sun appears white versus why the sun appears yellow. I bet you guys know the answer. I think you remember it, but let's just check. When does the sun appear white?
It appears white in space.
Good.
If I remember correctly.
And why?
If I remember correctly, it's because it may be outputting a lot of green light, but it's also outputting other colors. So when they mix together, it creates white light.
Exactly. It's blackbody light peaks green, but emits enough blue and red and thus appears white. Just like a blackbody light bulb appears white. When does the sun appear yellow?
That's in the atmosphere, and it's because of the tinge of the ozone.
Or from the ground. And why does it appear yellow again?
Because of the color of our atmosphere is.
Our atmosphere scatters the blue wavelengths of light.
Yeah.
It scatters them sideways, and that removes them from the sun's spectrum or from the image of the sun, from the ground. So blue wavelengths of light are scattered, that's the key term, are scattered by the atmosphere, leaving the sun yellowish. Good job, Ian. I like that you did that stuff. Now you'll be able to tell your kids why the sky is blue. It's because of Rayleigh scattering, okay? Jenna, you're on a roll, so I'm going to have you read 62 as well, all right? Let me just give Nori and friends a second to catch up. I need some water. I hope she made it out of the garage okay. All right, folks. You good? I'm gonna race. All right.
Okay, 62 is called pressure of the photosphere. The gas pressure of the photosphere changes substantially from its upper levels to its lower level. Near the top of the photosphere, the temperature is about 4,500 Kelvin, and there are about 1.6 times 10 to the 16th gas particles per cubic centimeter.
Sorry, what was the number density?
1.6 times 10 to the 16th.
And what were the units of that number density?
Gas particles per cubic centimeter.
So remember how we can write this. It's possible to write it as centimeters to the -3. Do you remember me telling you that on Monday?
Yes. Yep.
Okay, so I'm going to do that for brevities. That's particles per cubic centimeter, but particles aren't a real unit, so I can write it centimeters to the -3. By the way, this is what's called a plane parallel atmosphere. We're going to have 3 layers to the photosphere. We're going to subdivide the photosphere into a top photosphere, a mid photosphere, and a lower photosphere. And we're going to have a slightly different temperature and a slightly different density at each stage. What's the temperature of the mid photosphere?
5,800 Kelvin. And N is equal to 1 times 10 to the 17th particles per cubic centimeter. And the bottom temperature is 7,000 Kelvin. And 1.5 times 10 to the 17th particles per cubic centimeter.
Okay.
The question is,
you want us to calculate the pressure at all 3 levels, right? Okay. Jenna, I'm going to work with you a little bit on this problem. What formula do you think we want to use here?
The ideal gas law.
Excellent. But Jenna, I'm going to explain something that you guys might have missed here. And in fact, it totally baffles my mind why the book would have given you the number density. Actually, it doesn't really baffle my mind. Astronomers always like to work in centimeters, never in meters. And there's a reason for that that has to do with electromagnetism, and I don't want to get into it. But believe it or not, most professional astronomers don't work in MKS units. They work in a slightly different unit system called CGS, centimeters, grams, and seconds. It does make some calculations easier. In this case, it's not helpful, however, because this astronomer, who's an astronomy person, naturally felt like giving you the data in particles per cubic centimeter. But check this out. The ideal gas law is actually an MKS formula because the units of the Boltzmann constant are 1.4 times 10 to the minus 23 joules per Kelvin. Joules, there she is, okay. Joules are kilogram meter squared per second squared. So do you see the problem, Jenna? We can't go plug in cubic centimeters into this when you're using MKS because a joule is a kilogram meter squared per second squared. What are we going to have to do, Jenna?
Convert the centimeters to joules, or we'll have to do some type of conversion.
Yeah. Is the deadbolt unlocked? Okay, perfect. Hold on. Yes, we are going to have to do some type of conversion, but I want you to figure out what it is. That matters to me. Ian?
Would you just be converting the centimeters into meters?
Yeah, but it's not that simple here. This is why this is an interesting problem.
Because it's the cubed?
Yeah, the cube matters. We're actually converting cubic centimeters into cubic meters. And Ian, since you were sharp enough to see that, let's have you do that. Guys, I should be done in like 5-10 minutes. We're almost there. All right. Okay, so let's just focus on the top, okay? And before we calculate the pressure, let's set it up like this. We're going to get Ian to help us convert number density from particles per cube. Ian's like, why did I open my big mouth, right? Is that never volunteer, never raise your voice, always stay in the shadows, right? Okay, anyways, number density is 1.6 times 10 to the 16th, and we would write particles per cubic centimeter. This time I'm going to do it as 1/6. Now, I'm curious to see if you can figure out how to do this. Obviously, we need a division bar, right, Ian?
Yeah, definitely.
So,
well, you could probably put the centimeters cubed on the top. Would it need the negative though, since it's on the top?
no. If I had wrote it -3,
Yeah.
like I did here,
Yeah.
then you would put it on the bottom with the -3.
Okay, got it. So
Since I intentionally reverted it to 1 cubic centimeters so we wouldn't have to get messed up with the negative shit, okay?
Okay.
So your first instinct is correct. We want centimeters cubed on top. What do I want in bottom?
meters cubed.
Okay, now is the tricky part. What the hell is the conversion from cubic centimeters to cubic meters?
Would it not still be 100 since they're both cubed?
And let me explain why. This is about linear area volume. In a linear conversion, surely there are 100 centimeters in a meter. But think about it, Ian. If you multiply a meter times a meter to get a square meter, it's no longer 100 square centimeters.
Would it be 1,000?
Because you've got all of this, if that makes any sense. What do you think the number of centimeters are per square? What do you think the number of square centimeters are per square meter?
Is it 100,000?
100 what?
100,000. Sorry, centimeters cubed per meter cubed.
Hold on, wait, are we doing cubics or are we doing squares?
Cubed,
All right, fine. So,
right?
yeah.
Are we not?
Okay, let me just tell you how you do this, because you cube the conversion just like you cube.
Yeah, so that's what I was thinking. So if it was squared, it would be 1,000 centimeters, and then you would multiply it by 100, right? And
1 cubed is 1. 100 cubed is what? Look.
yeah, so 100 times 100 is, oh, I messed that up. It would be a million?
A million.
Okay, yeah,
Okay.
I dropped a 0, I think.
Without anything, if you increase this number by 1 million, what do you get? No calculation.
You would get 1.6 times 10 to the 22nd.
Good. And that's, now I'm gonna funky my units up again by doing meters to the minus cubed, okay? Now we can calculate the pressure of the photosphere. So let's go ahead and do this. The pressure at the top of the photosphere is the number density 1.6 times 10 to the 22 meters to the minus cube, whatever the crap that is, meters to the minus 3, times the Boltzmann constant in MKS units, 1.4 times 10 to the 23 joules per Kelvin. Guys, I put a negative up here earlier. Please get rid of that. Sorry about that. Wait. Actually, now I'm confused. Is it negative or positive? This is last night's whiskey talking right now, because I can't remember what the power of the
I
Boltzmann
have
constant
it
is.
written down as negative, but
Okay.
you can double check.
Boltzmann constant. Yes, it is negative. Sorry, I just totally backwards myself. Put the negative back in. All right, I had a moment of confusion, but it's gone. Times the top of the photosphere, which is 4,500 Kelvin. Okay, go, punch it up real quick.
I got 1,008.
Just go with 1,000.
Yeah.
And do you want what the units of this pressure are, Jenna?
Pascal.
Very good. Now, Jenna, do you remember what the atmospheric, that's the same as 1 kilopascal, right? That's another way to write that. Do you remember how many, what the pressure of Earth's atmosphere is at sea level? Does anyone? I told you that last time.
100,000 pascals or? Yeah.
Or 100 kilopascals.
Yeah, 100K.
So what percentage of Earth's atmospheric pressure is this?
1%.
Beautiful, right? The numbers are nice and simple. That's why this problem is cute. 1%. I'm just going to write ATM, 1% of our atmosphere, just because I want to speed this crapola up, as I'm sure you guys do. Okay, the next two we're going to go a little bit smoother because we already have our conversion factor. It's 1 million cubic centimeters per cubic meter. So I need to erase, okay, guys? Don't you forget those numbers on me, okay? Next up, we're going to do the mid-photosphere. Let's just go right into it. The pressure is going to be, first give me the number density in particles per cubic centimeter.
1 times 10 to the 17th.
And we now know, watch my maneuverings, it's 1 million per cubic meters per cubic centimeter. This is some highly offensive shit that we're doing here, okay? But it's valid. It's completely valid. Times the Boltzmann constant, 1.4 times 10 to the minus 23 joules per Kelvin, times the photosphere's mid-average temperature I have memorized is 5,800 Kelvin. You guys see how I put the conversion right into the ideal gas law? I'm just feeling lazy and I'm feeling like I want to be done and I want to like do anything else but this. I want to take a nap. Okay. So let's go ahead and calculate that up.
I got 8,100 or 8,000.
Yeah. 8,100 pascals, or roughly 8 kilopascals. And Jenna, the numbers work out so clean and beautiful because what percentage of Earth's atmosphere is that?
8%.
Yeah, that's why this problem is cute. It's 8% of the atmosphere at sea level pressure, okay? And now for our final coup de grace, to put this little homework number 7 to bed, we're going to do our final calculation at the bottom of the photosphere. And the pressure will be, can you remind me what the number density was?
Yep, it's 1.5 times 10 to the 17th centimeters
The
to the
minus,
-3.
we'll multiply that by 1,000,000 per cubic meters per cubic. Listen to that one. Per cubic meters per cubic centimeter. How you like that maneuver? Okay. Per cubic meters per cubic centimeter. That's messed up. Times 1.4 times 10 to the -23 joules per Kelvin. And what was it? 7,500 Kelvin for the bottom?
7,000.
Oh, just 7,000 Kelvin. Okay. All right. Punch him and crunch him. Punch and crunch. The peanut gallery is enjoying my witticisms here in the background. What'd you get, Jenna?
I got 14,700, which I guess we could do as 15,000.
Okay, sure. And you mean pascals, I think, right?
Yes, that's, yeah, absolutely.
Well, 15 kilopascals, or 15% of the atmosphere of sea level at Earth. You know what blows my mind about this problem? The entire photosphere, top to bottom, ranges from 1% to only 15% of the pressure and presumably the density of atmospheric gas, yet it glows just like this Bic lighter does. Truly, a gas must be very, very thin before it can transition into an emission kind of spectrum, right? Also, the so-called surface of the sun is actually pretty ghost-like and tenuous compared to the air we breathe in this room. All right. Well, you've done it. You've wasted another 3 hours learning about the sun. And please turn in your homeworks, your labs, get them all in. If you haven't watched the Monday lecture, Ian, you got to do that. Okay, guys. Next week, we start talking solar system stuff. Be time to look at some pictures of planets. It's going to get better and better right up into the end, okay? All right. Any other issues before I take off? Then I'll see you later. Bye.